Okay, so before we get started, my initial plan for this evening was to go through chapter 13 and 14 content review, and then to review the challenge problems that were posted on the SI information tab last night. However, I had all my work written out for all the challenge problems and left it in my lab notebook, and I just got home 30 minutes ago to realize this. Okay, so I'm actually currently writing out the answers to the challenge problems. I'm on problem 9 now, but this session will just be for the content review. I apologize for this. That was not my intention, but I live 40 minutes away, so going back and getting my work wasn't really an option. I have to rewrite it and then take pictures, get them into the slides, and then I can go over it. So I'll have to do a pre-recorded or like a recorded on my own session to go over the challenge problems for tonight. Okay, but I will make myself, I'm normally pretty good about email, but I'll make myself a little extra available in case you have any questions, because again, ideally I wanted to go through those challenge problems with you guys so that you guys could ask questions as we went. Okay, so to get started tonight, last Monday, there were 6 challenge problems given, but the first 4 kind of correlate to chapters 14. So I want to go over those, especially number 2 I want to go over. Okay, and all the problems, these 4 that we're going over tonight, are problems that were seen on my exam. Okay, so these are basically real multiple choice questions from an exam that's been given in the past. Again, I've made slight changes, but in this case, it's probably just the equation that I use that's different. Okay, so this question, they just wanted you to pick your conjugate acid-base pairs, right? So they wanted you to state what is the acid and what's its conjugate, and then what's the base and its conjugate. Okay, so if you didn't really get the formatting, the semicolon's supposed to split up the pairs. And again, if you didn't like the formatting, I kind of just kept it from how it was on the exam. I like to keep formats when I can. And so just be aware if the formatting didn't make sense to you, kind of how it was supposed to go. Okay, so in all the options, the first thing listed is dihydrogen phosphate, okay, which is on our reactant side, and that's going to act as our acid, right? And so I know that in commas next to it, I need to look for its conjugate base, right? Because the acid, once it loses that proton, becomes a conjugate base. Okay, so to find my conjugate base, I'm going to look on my product side. And again, remember our conjugate base is just our acid after that hydrogen has been lost. Okay, so once we take a hydrogen away from dihydrogen phosphate, it becomes hydrogen phosphate. Okay, so it should be H2PO4 minus paired with HPO4 2 minus. And so that's our acid and our conjugate base. Now our other pair would be our base and our conjugate acid. Okay, so looking at our reactant side, if dihydrogen phosphate's an acid, that means water has to be our base. Okay, and our conjugate acid, which will be found on our product side, will just be our base after it gained a proton, right? So it's going to be water once it gained a proton, which becomes hydronium. Okay, so hydronium is our conjugate acid. That makes choice E correct. Number 2, what is the pH of a 1.0 times 10 to the negative 10th molar sodium hydroxide solution? If you plugged it in normally, I believe you would have gotten 4, but I'll show you on the next page. And number 2, I remember created quite an uproar when I took this course because everyone kind of solved it the same way and kind of all of us got it incorrectly. Okay, so I just want to make you aware of scenarios like number 2, but the work's on the next slide. So we'll kind of come back to that in just a moment. Okay, but realize that the pH should have been slightly greater than 7. Now in number 3, they ask which of the following is true about the solution, and the solution should be neutral, right? We're adding strontium phosphate to water, right? Now strontium phosphate is just a salt, right? There's no hydroxide, there's no H+, like there's no hydrogen or hydroxide to lose, right? So, and so you can't really associate with an acid or base. Instead, we have a cation, which is strontium, right? A metal. And we have an anion portion, which is our phosphate, right? We're just adding a normal salt into it, and so it's a neutral compound. Okay, again, one like number 3 was on my exam, and really what this is testing is, yes, we're in an acid-base chapter, but can you sometimes take a step back, look at this salt and say, that's not an acid or a base, that's just a classic salt that we've been introduced to before. And so because it can't donate H+, again, it's a salt, it's not a base. So because it's not an acid or a base, our solution will be neutral. Okay, so again, kind of just be wary of that. Sometimes you might need to step back and kind of analyze, that's just a salt, it's not going to affect my pH in any way. Okay, but let's look closer at number 2. Okay, so we added 1.0 times 10 to the negative 10th molar sodium hydroxide, which is a strong base, meaning it's going to completely dissociate into 1 times 10 to the negative 10th molar hydroxide. Okay, so the mistake many people make, and when this was on my exam, this is exactly what I did, is I took the concentration of hydroxide, I plugged it in to find that my POH is 10, and therefore my pH had to be 4. Right? All of us, when we took it, thought this was the best question on the exam. We're like, oh, it's so straightforward, it's easy, we love it. Okay, but again, that is a mistake. Okay, the correct way to solve this problem is our calculations above were correct, that from sodium hydroxide, we do have 1 times 10 to the negative 10th molar hydroxide. Okay, but we're also adding this to water, and water as an intrinsic property has a concentration of hydroxide equal to 1 times 10 to the negative 7th molar, right? Neutral water has a concentration of 1 times 10 to the negative 7th molar hydroxide. And so our total concentration of hydroxide is those two values added together, which actually comes out to, when you add them, 1.001 times 10 to the negative 7th molar. And so when we plug this in for POH, our POH comes it's very slightly below 7, meaning our pH is very slightly above 7. Okay, and so again, the answer to this would have been slightly above 7. And this makes sense, right? Without looking at the numbers, if we have a neutral beaker of water, right, it's neutral, pH 7, and we're adding some sodium hydroxide or strong base to it, doesn't it make sense that it gets more basic instead of having a pH of 4? Okay, so this is kind of one where you have to step back, use a little bit of logic, and realize that water will also contribute to our hydroxide concentration here. Okay, I really specifically wanted to go over this evening because, again, this has appeared on past exams, and often students will say, oh, this is so straightforward. Let me just plug in my hydroxide concentration and get my pH. Okay, but ones like this, sometimes step back and think about the logic. Okay. Okay, and the last one to go over from Monday night's challenge problems is, again, a question that was on my exam, and it says the conjugate of a weak base is A. Okay, now again, we know that the conjugate is always going to be the opposite, right? A weak acid's conjugate is a conjugate base, and a weak base's conjugate is a weak acid. Okay, so kind of knowing that the conjugate of a base should be an acid, we should automatically be able to eliminate A and C. Now, the key point here is that your conjugate will never, ever be a strong acid or base, right? We, in this course, will never see a strong base or acid produced on the product side. And the reason for this is we assume strong acids and bases completely dissociate, meaning even if we were able to form strong acid or strong base, it would immediately split apart into its ions yet again. Okay, and so whenever we see a conjugate in this course, it's automatically going to be a conjugate weak base or weak acid. And because now we're looking at the conjugate of a weak base, we know it has to be weak acid instead of weak base. Okay, are there any questions on those 4 challenge problems before we get into the review? It'll be posted as soon as I can get it posted, but yeah. That's really, I can't really put a time on it, but as quickly as I can. Sorry, cursors. Question 2 really quick. Yes, I can go back very quickly. Again, these are also in Monday night sessions from this week. That's when the problems were given. Okay, here's if you wanted to see the solution for it. Okay, so I'm going to take this one question at a time because there are kind of a bunch. So I'm going to answer Anna's question first. If you started with a strong acid, the conjugate will be a weak base, correct? So I would argue no. So the conjugate of a strong acid is a weak base, technically, okay? But in the context of this course, the conjugate of a strong acid will actually be a spectator ion. Okay, and I'll talk about this more. I do have kind of a section in tonight's review that will talk about that. So hopefully my elaboration there will help make more sense of this. Okay, but your conjugate of a strong acid in this course will be a spectator ion. Okay, it's also technically a weak base. That's not really incorrect. However, on a multiple choice exam, if spectator ion came up, I think that's a pretty good answer. And again, we'll talk about that more later. Alyssa asked, is water always involved in questions like number 2? So acids are aqueous. So by nature, acids have to be in water. And so they might not state it. However, you should always assume that, which is why when we write equations with like a weak acid or a weak base, we react it with water. Okay, so we're always assuming that. And somebody else asked, how did I know the concentration of hydroxide in water? That is a constant. That is always a given. Unless they tell you the pH is not 7, we always assume water has a pH of 7. Okay, and so in neutral water, you have equal amounts of H plus and hydroxide. They have to multiply together to equal your Kw, which is 1 times 10 to the negative 14th. That's a constant. Alyssa, you asked a follow-up question. I'm just not quite sure what you mean by that. So if you elaborate a little bit more, I'd be happy to comment. Oh, okay, I answered it. So Josh asks, are you supposed to account for water every time you calculate pH? No. How you do it is typically correct. However, again, step back and think of the logic of this, right? You have neutral water with a pH of 7. You're adding base to it, but based on your calculations of this, you have a pH of 4. Okay, that's not physically possible, right? When you add base to a neutral solution, you have to have a basic solution. Okay, and so in this case, you do need to account for the ionization of water. Okay, this is basically the only type of problem you'll have to account for that. However, I don't know. I want you to be familiar with this question. Again, it's something that appeared on my exam. I would say about 80% of the kids got it wrong. So now you've been exposed to it, and just keep it in the back of your brain. You know, don't lose all confidence in how you've answered questions up to this point because of this one question. Okay, just be aware, right? If you calculate something this easy and you realize, hey, I just added base to water and you get 4, that should be a little alarm going off in your head saying that's not possible. And Amy asks, how do I know that the salt in question 4 wasn't an acid or a base? I mean, it has 0 protons, it has 0 hydrogen in it, so it physically cannot be an acid. And it's just a salt, you know, it's a cation and an anion together. There's no obvious hydroxides or H pluses. That leads you to say it's neutral, right? It's not a weak base. Weak bases we typically see nitrogen involved with. Yes, there are other ones, but if they just throw at you some really random salt and say kind of a question like this, what's the solution in terms of acidity or basicity? They're just trying to throw you off. It's salt. Your solution's neutral. Any other questions before jumping into the review. Okay, again, these 4 challenge problems that I went over tonight, especially ones like number 2 and number 3, they're just scenarios to be aware of, right? Sometimes people are so used to just doing ice tables in chapter 14. All you see is numbers, 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 X, ignore X, you know, whatever, pH, POH. Sometimes take a step back on exams, okay? Like question 2, again, if you're just looking at the numbers, yeah, you'll get a pH of 4. But step back and actually just think about the logic of these solutions. Okay, and so anytime you have a really easy or a question that looks really easy, like number 2, I suggest that those are the ones especially that you take a second on and say, are they throwing any curveballs without me realizing it, right? Again, adding base to a neutral solution and getting an acidic pH is a curveball, right? There you had to make the jump and say, you know what? Water's concentration of hydroxide actually has an effect here. Right? During our normal problems, the amount of H plus or hydroxide from water is negligible, right? It's so little compared to how much is normally in the solution, it doesn't actually have an effect. But in questions like number 2, it does. Okay, so now that I'm kind of done with my little rant, let's jump right into chapter 13, okay? So we started off in chapter 13 learning about equilibrium. Right? So our equilibrium constant we denote with K. In general, it's a ratio of our rate constant of our forward reaction divided by the rate constant of our reverse reaction. Okay? Also, generally speaking, it typically means amount of products divided by amount of reactants, right? It's kind of an oversimplification, but you can think about that. It's products over reactants. And then when we actually want to calculate it, right, we're going to do the amount of products, and we're going to raise it to its coefficient, right? So compound C, its molarity will be raised to whatever its coefficient is in the balanced chemical equation. Okay, we'll multiply that concentration by the concentration of D, which is also a product, raised to its coefficient from the balanced chemical equation. And then in the denominator, we'll do our reactants, right? So our reactants raised to their respective powers. Okay, now we can solve for the equilibrium constant in terms of molarity, right? So in terms of concentrations, or we can do it in terms of gases, right? And we're gonna plug in pressure in terms of atmospheres when we do gases. Okay, now it's kind of a small point that at this at this stage in the game we kind of overlook, but just be careful that you do not include, right? You do not include any reactants or products that are liquids or solids. Okay, so not include or exclude, meaning the same things. So you leave out solids and liquids from the equilibrium calculations. Okay, if you're ever asked to solve for K, the equilibrium constant, right, just realize it has no units, right? So it's just going to be a numerical value. And then I've emphasized this pretty much every time I've talked about this equation, right? But if you don't have this equation, I'd write it down because I do not think it's on your equation sheet. Okay, it's one of the few equations you might need that's not on the equation sheet. What this equation does, it allows us to convert between our equilibrium constant in terms of pressure and our equilibrium constant in terms of concentration, right? That's what the P and C stand for. Okay, now the RT section, so R is our ideal gas law constant, so it's going to be that 0.08206 value, and it's going to be multiplied by our temperature in Kelvin, right? Remember to convert to Kelvin. And then R times T is going to be raised to the delta N power. So whenever you see delta N, it means change in the number of moles of gas. Okay, and remember that delta, right, this triangle, is always final minus initial, which in the context of a chemical equation will be products minus reactants. Okay, so if we combine these together, delta N means you're going to take your moles of gas product, right? So how many moles of gas do you have on your product side? And you're going to subtract from it the number of moles of gas on your reactant side. Okay, and so when you do that calculation, you'll get delta N, which is your superscript or exponent for the R times T portion. Okay, this equation doesn't come up too often. Okay, so I wouldn't be surprised if you don't see it on the exam tomorrow. However, you could, and it's not on your equation. Kc just stands for your equilibrium constant in terms of concentrations, right? It means that your reactant and products were in terms of molarity. Okay, Kp means that you plugged in a bunch of pressures because they're in the gas phase. Okay, and so typically when we solve, we just write K, and if they gave you pressures, you plug in pressures. If they gave you concentrations, you plug in concentrations. But those two values will be different, and you can use one to solve for the other. Again, pretty rare to have to do, but be familiar with it. At least have it down on your notes. Okay, we also learned in chapter 13 about the reaction quotient, which we denote with the letter Q. Okay, and basically what this does is it tracks our direction and our progress towards equilibrium. Okay, in terms of how to calculate Q, right, we're going to calculate it in the same exact way that we calculate K, our equilibrium constant. Okay, but we use Q, we use this reaction quotient when we don't actually know if we're at equilibrium or not. Okay, and so I'm sure by now you guys are pretty familiar with the questions that I've provided and also your professors, where they'll actually give you your equilibrium constant, and then they'll give you values of your reactants and products to find your reaction quotient, Q, and then they want you to do this comparison to make a comment about the direction of the reaction. Okay, and so before I go through the direction, just remember that Q generally is products divided by reactants. Okay, and so if our Q is less than our equilibrium constant K, right, that means, right, Q is too small. That means we have too many reactants and not enough products to be at equilibrium. Okay, so this means that the forward direction or the forward reaction will be favored, okay, which is our typical left to right. Okay, if Q is equal to K, that means that we're at equilibrium. Okay, and then lastly, when Q is greater than K, right, generally speaking, that means you have too many products and not enough reactants to be at equilibrium. And so our reverse reaction or the reverse direction will be favored, which is when we're looking at an equation, that would be right to left, right? It would be our products are being converted to reactants. Okay. Okay, here's another topic that isn't seen too often, right? I'm sure you haven't seen too many examples where you have to manipulate K, but it does have a habit of sneakily finding its way onto the exam. Okay, so I would definitely expect maybe one multiple choice question to address manipulations of our equilibrium constant. Okay, and I have provided maybe one or two challenge problems in the past that addresses this, and one for tonight's, out of tonight's, or the challenge problems I posted yesterday is also a manipulation of K problem. Okay, and so really we just need to know how we manipulate K in response to three different changes or three different manipulations. Okay, and so the first thing could be we might need to reverse a reaction. Okay, so if we have an equilibrium constant of 4.36 for the reaction of A getting converted to B, okay, what would our new equilibrium constant be if we wanted to reverse the reaction? Okay, so if we want the equilibrium constant for the reaction B goes to A, what we're going to do is take the inverse of our old K, right? So our new K for this reaction B goes to A would be 1 over 4.38, which is equal to 0.228. Okay, so that would be our new K value. Okay, well, if we need to multiply an equation by a coefficient, whenever you do this, you're going to take your original equilibrium constant and raise it to that coefficient. Okay, so for 2a goes to 2b, right? We just took our original equation and multiplied it by the coefficient of 2, which means our new equilibrium constant is going to be equal to our old equilibrium constant raised to that coefficient. So it's going to be squared in this case, because that's what I multiplied my equation by to get this new one. And so my adjusted equilibrium constant for this equation would be 4.38 squared, which is 19.18. And then lastly, if you ever need to add two reactions together and they each have their own equilibrium constant, when you add the reactions together, you're going to find your new equilibrium constant by multiplying your original equilibrium constants together. Okay? Which, when you kind of come back, that makes the multiply by a coefficient manipulation make a little bit more sense, right? If we have the equation A goes to B, and we add it to itself, right? A goes to B plus A goes to B. According to this third rule, we'd multiply their k's together, which would be 4.38 times 4.38, which is just 4.38 squared. Okay, so these last two can kind of make each other make sense. No, you never need to subtract. Okay. Okay, so reverse reaction, you're going to take the inverse of K, multiply by a coefficient, you're going to raise it to that coefficient, your old K, and then add your equations, you're going to multiply your Ks. Somebody asked, when would you do K raised to the 1/2 power? That would fall under the second rule, right? You would do that if you multiplied your whole equation by 1/2. Okay, so let's say our original equation was 2A goes to 2B with an equilibrium constant of 19.18. So if we wanted to find the equilibrium constant just for A goes to B, we would do 19.18 raised to the 1/2 power, right? Because we're basically taking this equation and multiplying it by 1/2. Okay, any other questions on manipulations of K before moving on? I believe we're just going to talk about general types of problems and then Le Chatelier's principle for this chapter. Okay, if there's nothing else, again, feel free to keep putting things in the chat if something does arise. Okay, so just some general types of problems that you see in chapter 13 to be wary of. Okay, so we have our classic table problems, right? These are the ones that you'll be given your reactants and products, and lots of values within the table will be missing. Basically, what the professors want you to do is fill out the table, right? And I mean, you can read these bullet points that I have, but basically you want to fill out the table until the end, or until if there's a spot that says you are at equilibrium, you just want to fill it out to there. And then typically in this classic table problem, you'll want to plug in your concentrations or pressures to solve for your equilibrium constant. Okay, so the table problem I'm referring to is the ones where you're missing lots of data, right? You're missing concentrations or pressures. You're asked to fill out the table, and then you're going to use, the concentrations and pressures to solve for equilibrium. So I've gone over lots of table problems in previous SIs, so I'd recommend going back. We've probably done 3 or 4 different ones all the way out. There'll also be one in the challenge problem review tonight. However, you know, as this is a PowerPoint, it's already pre-made, and so I don't have any table problems to really go over. So again, look at previous SIs or email me or something, and we can figure something out. Okay, so Ariana in the chat asked, if you're given a value for a liquid at a time interval, can you use it to determine X and find values for other concentrations? I would say that if you're put into that scenario, that's what you should do. However, you probably won't be put in that scenario, right? Because they're going to be giving you pressures or concentrations of reactants and products. And so if one of your reactants or products is a liquid, the concentration, like the molarity or the pressure, gets really weird. And so I would say there's such a minuscule chance of them giving you information about a liquid. Okay, and if you're referring to a previous problem I've given out, If in the chart I had a liquid, it was by mistake. I do not know at all what sessions. Anyone that I covered chapter 13 on, though. Okay, so before February 25th. Sorry, just trying to go in order so I don't leave any questions. Sorry. Lizzie asked, if you don't indicate when equilibrium is, how do you know where equilibrium is? And that's a great question. What I'd say is if they give you no indication of where equilibrium is, it's going to be the last data set in the chart, right? It's going to be all the way to the right if they give you no indication. Okay, other ways they can indicate where equilibrium is they could tell you, right? So instead of, 1 hour, they might physically write equilibrium. Or the last way, and this is kind of a way that you'll see in tonight's challenge problems, sometimes your concentrations or pressures won't actually change from, one interval to the next, right? And so in those cases, if your pressures or concentrations aren't changing, you can assume you're at equilibrium. And an example of this, Dr. Katie went over in lecture back in chapter 13, right? So we had a giant chart. In the last maybe 3 time intervals, the concentrations or pressures barely changed. And so that was the indication that you're at equilibrium. Sorry, there's just a lot in the chat and I'm trying to read and answer. Jesse, no. Probably not. I don't really know what that means. pH of water would affect the ice table. You could be, it's just kind of hard to, so I'm just going to say no to your question, Jesse. Sometimes they'll give you a pH of solution and you need to use that in reference to your ice table. But no, if you're talking about like questions like the challenge problem number 2, if you're afraid that's going to impact your answer, no. How you've been solving for all the problems in the past are correct. What I showed in question 2, I know it kind of throws you for a loop. Realize that that's such a small exception that just don't worry too much about it. Are the challenge problems? Yes, all the challenge problems. See the announcement. I talked about where the challenge problems are. They're on the SI tab. I don't remember what I labeled it though. Okay, so going to the other types of problems. Sorry for kind of getting off track. If people keep putting questions in the chat, I'll get to them after talking about this slide. Right, so we kind of talked about general table problems. Now in chapter 13, we also introduce ice tables. Okay, and so in the classic chapter 13 ice tables, which are definitely easier than the chapter 14 ones, right, they'll typically give you a starting concentration of a reactant, and they'll also give you your equilibrium constant. Okay, so what you're going to do is you're going to make your normal ice table and write the change in terms of X. Once you write the change in terms of X, you're going to write your equilibrium concentration in terms of X. Okay, and using your equilibrium constant, which again, in a typical ice table question, that's given, right? You're going to use your equilibrium constant to solve for X and then answer the question. Okay, also seen in chapter 13 are questions where they ask about solids or liquids, right? So this type of question is almost always an ice table question, okay? And typically they'll give you your equilibrium constant in terms of pressure, okay? And so when you solve for X, you'll be solving for the pressure of a product, right? Some of your products will be gases. Once you solve for the pressure of your gas, which is a product, which again will be equal to X, right? You can use the ideal gas law to convert to moles of that gaseous product. And then you can use your stoichiometric ratio from your balanced chemical equation to solve for moles or grams of solids or liquids. Okay, and so this is kind of the process that you use anytime that they ask you about a solid or liquid in an equilibrium question. I'll talk about the challenge problems at the end. And Alyssa asks, when doing ice table questions, can we leave out everything that isn't a gas? Sort of. I would say you can leave out anything that isn't a gas or in the aqueous state, right? But you can leave out in your ice tables any liquids or solids, right? Because ice tables, we really only look at things that affect equilibrium, which is K. Okay, lastly, the last topic in chapter 13 that we're going to touch upon is Le Chatelier's principle. Okay, and so I basically call this chemical homeostasis, right? Homeostasis is basically your body's attempt to stay at a particular set point, right? So our temperature is around 98 degrees, right? Our body temperature. And so if our body starts to get too cold, right, we have homeostasis and we will shiver. And the act of shivering will actually warm up our body temperature, right? We're trying to resist the fact that our body temperature dropped below where we want it to be. Okay, on the other end of it, right, if we get too warm, we start to sweat. And that's, again, our body's attempt to cool us down to remain at our normal temperature of around 98 degrees Fahrenheit. Now, Le Chatelier's principle is basically the same thing, but looking at chemicals and compounds, right? When a system or a reaction is at equilibrium and we put on it some manipulation or some change, right, the system's going to shift to counteract that, right? It wants to stay at equilibrium, so it's going to counteract our change. And so the manipulations that you should understand are when you add a reactant or product, when you remove a reactant or product, when you change the volume or the pressure, or when you change the temperature. Okay? And so if you add a reactant or product, you're going to shift in the opposite direction. Okay? So if we add reactant, we are going to shift towards the product side in order to resist the addition of that reactant. Okay? If we remove a reactant, we are going to shift towards the reactant side, again, in order to resist the change. Okay, realize that pressure and volume are inversely related. Okay, so if the volume increases, the pressure is going to decrease. And if the volume decreases, the pressure is going to increase. Okay, so realize that if they talk about pressure or volume, they're inversely related. Okay, and oops, sorry about that. And how do we resist changes in pressure? Well, to look at how our system will change based on pressure changes, we have to look at moles of gas. Okay, so we're going to look at how many moles of gas we have on the reactant side and the number of moles of gas we have on the product side. Okay, if the pressure increases, we are going to shift to the side of the equation that has less moles of gas. If the pressure decreases, like if we decrease the pressure of the system, our equation is going to adjust by shifting to the side that has more moles of gas. Okay, if you have equal numbers of moles of gas on both sides, changes in pressure or volume will not shift it one way or the other. It'll be no effect. Okay, that's if there are the same number of same number of moles of gas on the reactant and product side. Okay, lastly, how about temperature changes? So in relation to temperature, I always suggest that students write heat or temperature into your actual equation. Okay, and so if you have an endothermic equation or an endothermic reaction, heat or temperature is going to be a reactant. If you have an exothermic reaction, heat is going to be written as a product. Okay, once you write heat as a reactant or product, right, if you increase the temperature, it's like adding reactant or product. If you decrease the temperature, it's like decreasing the amount, it's like removing reactant or product. Pressure and volume are indirectly proportional. Ideal gas law, right? PV equals nRT. Somebody put in the chat 1 over whatever. I'm just not sure what that is. If you add a reactant or product, you shift in the opposite direction. If you remove, you shift to that direction. Okay, so you add reactant, you shift to the product side. You remove reactant, you shift to the reactant side. Correct, catalyst changes nothing. Okay, and again, in chapter 13, pretty much every session I went over about a 5 to 6 part Le Chatelier's principle question. So if you review all the times we went over that, I'm sure you will pretty much have seen every, really any possible scenario that they can throw at you. Okay, Caitlin asked if there aren't any delta H, if there isn't a delta H given, would temperature have an effect? So temperature will always affect equilibrium. Okay, so they're going to somewhere indicate whether it's endothermic or exothermic. If they truly do not give you an indication, then your answer would be needs more information. Okay, you'll often see in previous examples, I've given that as an option. Okay, and so if they don't tell you if it's endo or exothermic and they ask how an equation is impacted by a change in temperature, and again, they don't tell you if it's endo or exothermic, you need more information, because whether it's endo or exothermic greatly impacts your answer. To Alyssa's statement in the chat, you are correct. If reaction is endothermic and I wouldn't say heat is added, I would say temperature is increased. Okay, and if you increase the temperature, it's like heat is added. Okay, but it'd be phrased as the temperature increases, the reaction is endothermic, thus you do shift to the product side. And Anna asked, how do you know if it's endo or exothermic if it just says the temperature decreases? If all they say is the temperature decreases, that does not at all tell you whether it's endo or exothermic. Okay, they're just saying that the temperature is decreased around you. Okay, they would have to tell you some other piece of information. Okay, any remaining questions on chapter 13 before we move on to our review of chapter 14? Okay, I don't see anything, so we'll just jump right in. Okay, so our acid-base definitions. So I'm sure by now we're pretty familiar with acids give up a proton or give up a hydrogen ion, while bases will accept these protons. Okay, we remember from our discussion both last semester and this semester that strong acids and bases will completely dissociate into their ions. Okay, if we have 10 molecules of a strong acid, they will split up into 10 molecules of H plus and 10 molecules of the anion portion. Okay, and so for acids, we have 6 strong acids that you should be aware of, and you should know all of these. Okay, so if you don't memorize them, please write them down on your cheat sheet, okay, because you are expected to memorize the 6 strong acids. Okay, so they're hydrochloric, hydrobromic, hydroiodic acid, right? So these are halogens, right? Notice that the only halogen not present here as a strong acid is HF. Okay, hydrofluoric acid is a weak acid. And then our 3 other strong acids are sulfuric acid, perchloric acid, and nitric acid. Okay, our strong bases, as a rule of thumb, are most things with a hydroxide group, right? So typically we see group 1 and group 2 metals with hydroxides, and those are our strong bases, right? So calcium hydroxide, potassium hydroxide, sodium hydroxide, strontium hydroxide, barium hydroxide, right? If you see hydroxide, it is way more likely than not, a strong base. Okay, and just remember our conjugate acid is what is left of the base once it's gained a proton, and our conjugate base is what's left of the acid after the proton is removed or lost, right? So in this example equation down here, we have cyanic acid, right? So it has a hydrogen. It's going to be our acid. So this is our acid. If cyanic acid is an acid, that means the other portion, water, needs to be a base. Okay, now my cyanic acid on the product side, once it loses that proton, is going to be my conjugate base. Okay, so cyanide is my conjugate base. While my water, which was originally my base, once it gains a proton from the acid on the product side, it's going to be our conjugate acid. Okay, so again, be familiar with being able to label these. That could on its own be a multiple choice question you see tomorrow, potentially. Again, I don't make the exams, I'm not sure. Equilibria of acids and bases. Okay, so kind of coming back to water, right? Remember that water has an intrinsic ionization. It auto-ionizes into H plus and hydroxide. Okay, its equilibrium constant, which we label as Kw, is equal to 1 times 10 to the negative 14th. Okay, so when we multiply the concentration of H plus and the concentration of hydroxide, it's always going to equal this Kw number. Okay, if a solution has more H plus than hydroxide, it's going to be an acidic solution. If it has more hydroxide than H plus, it's going to be a basic solution. And if we have equal amounts of these two ions, then because of the Kw, their concentration will have to be 1 times 10 to the negative 11th, which is a neutral solution of water, right? And so if we're just adding something to water, right, we're assuming the water is neutral, okay? And again, for the majority of your problems, I would say 99% of your problems, this auto ionization of water doesn't impact your answer, okay? It's just in the very rare occasion you see a problem like the second challenge problem we went over at the beginning of tonight's session that you might have to factor in the auto ionization, okay? But for 99% of your math problems, you do not need to factor it in. So Rachel asks, if the problem gives you the concentration of hydroxide in pure water, do we set it equal to H plus, or do we divide it by 1 times 10 to the negative 14th? So if you're told you have pure water, they probably won't tell you the concentration of hydroxide, right? Because pure water, by definition, will have a pH of 7, and therefore you automatically know that H plus and hydroxide will have a concentration equal to 1 times 10 to the negative 14th, okay? And so that would kind of be known. What I think you're kind of alluding to is what happens if you have a water solution that has a pH not equal to 7? Well, in that case, you can use the pH or POH to solve for the concentration of H plus or hydroxide, and then you can use the Kw to solve for the concentration of the other component. Okay, hopefully that answers your question, and just let me know if it didn't. Okay, and equilibria, I'm sure we're very familiar now with our acid dissociation constant, our Ka. Really all this is, it's our equilibrium constant for a weak acid. Okay, and how we set this up is our equilibrium constant, our Ka, is equal to the concentration of our products divided by the concentration of our reactants. Okay, and remember that Kb is exactly the same as Ka, it's just for a weak base, right? So if a weak base is on your reactant side, you're going to use Kb instead. Okay. Somebody just asked a question that I think is answered on this next slide. So I'll kind of I'll elaborate and then I'll check the chat to answer more questions. So here's some really important equations that, again, if you're not familiar with these, definitely have them written down. you'll need to use these equations all across your exam tomorrow. Okay, so one relationship that will always hold true is that whenever you multiply the concentration of H plus by the concentration of hydroxide, it always has to equal 1 times 10 to the negative 14th. Okay, and this same relationship holds true for Ka and Kb. Whenever we multiply Ka times Kb, it always will equal 1 times 10 to the negative 14th. Okay, so using this relationship, right, you can typically, a classic problem is you'll need Ka to solve a problem, and your professors will give you the Kb. And so you'll have to use this relationship to solve for your Ka and then go on with your problem. Okay, we also learn in this chapter how to solve for pH and pOH. Okay, so remember, whenever we see a small p in front of something in chemistry, it means take the negative log of. Okay, so pH means take the negative log of our hydrogen concentration, right? pOH stands for take the negative log of our hydroxide concentration, right? Thinking about chapter 15, when we find our pKa, that means take the negative log of our Ka. Okay, so whenever you see that small p, it means take the negative log of. Okay, so that's how you find pH and pOH. And here is kind of our last really, really important relationship. Whenever we add pH and pOH together, they'll equal 14. Okay, and here are some constraints that show you an acidic and basic solution. Okay, before going into the chat and answering any questions that I haven't been able to address yet, I just want to make one comment so that you're aware of it. Okay, so if you actually plug in to your pH equation a concentration of H plus of 1 molar, okay, so 1 molar concentration of H plus, when you solve for your pH, it will actually come out to 0. Okay, if you plug in 2 molar for your concentration of H plus, when you solve for your pH, it will actually come out to a negative number. Okay, so just be aware that it is possible to have a negative pH or pOH, okay? You don't see that in a lot of problems. It's pretty rare to see, but just be aware that it is possible, okay? So if you plug in like 5 molar for your concentration of H plus and get a negative pH, just realize that that is possible and it doesn't mean it's wrong necessarily, okay? So just be aware of that, okay? Even when we have negative pHs or pOHs, this relationship, pH plus pOH, will still stand true, right? So if our pH is -1, our pOH would be 15, okay? Again, just be aware that that is possible. One problem said if OH equals 6.8, then H plus equals 6.8, and that using KW wasn't the way to go. I don't know what problem that is, so I can't comment. Yeah. No, I said, so Ka, the A portion stands for acid. Okay, so you only use the Ka when on your reactant side, you are dealing with a weak acid. You're going to use your Kb when on your reactant side you have a weak base. Okay. So if your pH is negative, it actually means that you are scary acidic. Okay, like burn your hand off acidic. Okay, and so the whole relationship stands true that a neutral pH is 7 and any pH below 7 is acidic, including negative values. Okay. In terms of the 6.8 question still, I think a couple people in the chat are alluding to it, but I'm kind of having a hard time following it because there's comments between. So if you want to talk about that question at the end, I'd be happy to do so. Somebody asked, what is the general equilibrium reaction for bases? I always suggest if you start with a weak acid or a weak base, always react it with water, okay? And the rest of the reaction should carry out, and you should get the correct products, right? So whether you start with a weak acid or a weak base, react it with water, and then you'll get the corresponding products, sorry. Okay, moving on to the 5% rule. So again, we can use the 5% rule for ice table problems, right? Whenever we're solving for X, whenever we're given the equilibrium constant, right? We're typically asked to use the quadratic formula in order to solve for X. Okay, but plugging values into the quadratic formula not only is time consuming, but it can also be error prone. Right, I know you guys can now use graphing calculators, so it's a little harder to be error prone now, but in general, the quadratic formula is error prone, which is why we have the 5% rule. And whenever we use this 5% rule, we're making a big assumption. We're saying that X is really small compared to initial concentrations or pressures. And so therefore, if X is so small compared to our initial value, whenever we see A plus X or A minus X, we can ignore the X portion and just write A, right? Because X is so small that it actually doesn't affect the value of A. Okay, that's the assumption we're making. And so once we ignore X, we can go and solve for the value of X, because we'll still typically have X in the numerator. And then once we solve for X, we need to do a check, right? We have to do X divided by our initial concentration of acid or base. And we multiply it by 100 to turn it into a percentage. When you do this check, if your value comes out to less than 5%, then your initial assumption was valid and the value of X that you solved for, sorry about that, was correct. Okay, so you can continue solving the problem. However, if you do the check and it comes out to a percentage greater than 5%, then it means that this valid is not, this assumption is not valid, right? The value of X is big enough that it actually will affect our initial concentration, whether we're adding or subtracting from it. Okay, and so if you do the check and it comes out to greater than 5%, you actually need to go back and solve it using the quadratic formula. Okay, if you prefer to solve it through the quadratic formula, you will get it right either way. Somebody asked if it's not a strong acid, do we assume it's a weak acid? Yes, right. If you can tell that a compound is an acid, if it's not one of those 6 strong acids, automatically assume it's a weak acid. Okay, here's just a slide to talk about polyprotic acids a little bit. So polyprotic acids are just acids with multiple protons. So diprotic acids have 2 protons or 2 hydrogens. Triprotic acids have 3 protons or 3 hydrogens. Okay, and so just realize that these polyprotic acids have an equilibrium for each proton lost. Okay, so for carbonic acid, we're going to have 2 different equilibriums, with the first one being the loss of the first proton, and the second equilibrium, we lose the second proton. Okay, something like phosphoric acid would actually have 3 separate equilibriums. Okay, and this is one of the challenge problems I gave out yesterday, just so you could be introduced to a triprotic acid question. However, you're much more likely to see a diprotic acid question tomorrow, and it will probably be 2 multiple choice questions on your exam. The typical question, which is what I'd anticipate you see tomorrow, is they give you the initial concentration of your diprotic acid along with your equilibrium constants. Okay, and they will ask for your pH and typically the conjugate base of the second equilibrium. Okay, and so again, we've gone through a bunch of these in SI. I also think Dr. Katie's lecture on polyprotic acids is, if you haven't seen the video, I definitely recommend it. I definitely think it's worth your time to re-watch it tonight if you don't feel fully good with polyprotic acids. I think Dr. Katie explained it really, really well. Somebody put in the chat that the quadratic formula gives 2 answers. It says usually sometimes with one of them being 1. So when I use the quadratic formula to solve for x, I have never actually gotten one of the answers as 1 in this course personally, so I can't really comment on that portion. However, when you solve for x, you're correct. You will get 2 answers. Usually, one of them will be negative, okay? And typically, it's the negative one that doesn't work. But what I suggest is once you solve for x, plug them back into your ICE table, okay? And when you plug both values into the ICE table, if either one of them gives you negative values at equilibrium for reactants or products, that answer is not possible. Okay, only the x value that gives you positive answers at equilibrium for all of the reactants and all of the products in the aqueous state, only that will be the correct x value. Okay, and again, there's a challenge problem tonight that will kind of address that. So somebody asked, will they go until they give up both or all 3 protons? Okay, so this is talking about di and triprotic acid problems. That's kind of tough. So that's actually a very complex question, and it's more of a biochemistry and upper level chemistry class. So I'm not really going to fully answer it. In this course, we kind of start with the first equilibrium, and we just kind of solve them as 3 separate ICE tables all the way through. Okay, it is much more complex than that. But again, that's more of an upper level chemistry, biochemistry question. Okay, are there any questions before I move on to kind of the second half of chapter 14? Also, are there any questions that I've missed up to this point? I've really tried to hit on every question, but I hope I didn't miss any. But you know, when a bunch are sent, sometimes I miss out on stuff. Okay, so let's take a little bit of time to talk about the strengths of acids and bases. And we're actually going to talk about this for a little bit because lots of students sent me emails, and I had some pretty good back and forth conversations with students yesterday about this topic. And so because multiple students approached me about it yesterday, I think that this is more of a widespread misunderstanding that I'm sure many people can benefit from a discussion about. Okay, so in general, strengths of acids, how do we describe them? Okay, so what we say is that the higher the Ka, the stronger the acid. Okay, and so strong acids like HCl and HBr, they actually do have a Ka, but it is extremely high, right? You can say HCl down here, the Ka is 1.3 times 10 to the negative 6th. Okay, this Ka is so high that when you actually go through all the calculations, basically you find out that every single molecule of HCl splits into its ions. Okay, and so again, the higher the Ka, the stronger the acid. And this makes sense when we think of what Ka means, right? Ka in general is products over reactants. And so if we have a really high Ka, that means that our acid dissociated into its ions and very few stayed together as an acid. Okay, so again, the higher the Ka, the stronger the acid. Okay, another phrase that we say is the stronger the acid, the weaker the conjugate base. And I think this is where a lot of students got confused. Okay, and so to exemplify this, let's look at 2 acids, hydrofluoric acid and hydrochloric acid. Okay, and so what I did is I listed their Ka values. Okay, so here they are. And I also listed their conjugate base. Okay, and I kind of put conjugate base in quotation marks, you know, at my computer screen, which you can't see. Okay, so F minus is the conjugate base of hydrofluoric acid. In this case, and here's the Kb value, right? We know it because Ka times Kb will always equal Kw. Okay, now as Kb gets bigger in value, that means that the base is stronger. Okay, so as we can see, the Kb for F minus is bigger than the Kb for Cl minus, meaning the conjugate base of fluorine, like fluorine as a conjugate base, is a better base than Cl minus. Okay, and yeah. Okay, and so that's kind of how you can apply that logic. Okay, now in the case of Cl minus, right, this is actually such a weak base, right, because it comes from a strong acid. Cl minus is actually such a weak base that we don't really consider it a base at all, right? We almost more consider it a spectator ion, okay? And that's because it's not a conjugate base, it technically is, but it's such a poor base that we basically pretend it's not one. Okay, now some general strength trends for binary acids. So the strength of an acid will increase with increased electronegativity. Okay, and so binary acids only have two portions. They have a hydrogen and they have an anion portion, right? So Cl minus, Br minus. It could be other anions as well. Single atoms with a negative charge as well. And so the general rule of thumb here is as the electronegativity increases, so does the strength of the acid. Lastly, oxyacids. So these are basically the acid forms of your polyatomics. And so the general rule of thumb is that the more oxygens there are, the stronger the acid. Okay, so per bromic acid with 4 oxygens is going to be the strongest, while hypobromous acid with only a single oxygen is going to be the weakest acid of those 4. Okay, let me just try to answer questions that came up. Oh, okay. So the question in the chat is, how would you use percent ionization to determine the strength of an acid? I'll talk about that in a couple slides when I bring up percent ionization. Okay. Okay. So I'm going to just kind of walk through this with people to kind of practice conjugate acids and bases. I sent this to a student via email yesterday, so I really apologize for the terrible photograph of it. This was also in my lab notebook that I left in lab, so I couldn't take a nicer picture of it. But this kind of walks you through how to write a net ionic equation, and it kind of makes sense of I think it helps make sense conjugate acids and bases. Okay, so when writing a net ionic equation, we can look at it as the product side and the reactant side. Okay, so something to keep in mind for the product side is we're going to assume that all salts dissociate 100%, right? So remember, a salt is any compound with a cation positively charged portion and a negatively charged anion portion. Okay, that aren't H plus or hydroxide, right? It'll be a metal and a non-metal. Now on the reactant side, right, if we see a strong acid or base, we're going to assume that they dissociate 100%. And if we have a weak acid or base, we're going to assume that they do not dissociate completely. Okay, and so the key thing about writing a net ionic equation is that if the compound dissociates 100% and is in the aqueous state, we're going to write it as their respective ions, right? So we're going to show them as splitting up into their ions. Okay, and so that's kind of the key to how to write a net ionic equation. And keep in mind that we consider something a spectator ion if it appears the same on both sides of the equation. Okay, so keep that in mind. Okay, so let's look at strong acid and strong base reacting. Okay, so we're going to have HBr, a strong acid, reacting with calcium hydroxide, a strong base, and this is going to go to form water and calcium bromide. Okay, and so again, I have a strong acid and strong base, and on my product side, I have a liquid, which I'm going to kind of just ignore, and I have a salt. Okay, now because my acid and bases are strong, and my salt dissociates 100% as well, right? All three of these species that aren't water are going to completely split into their ions. So what I do is I rewrite the same equation, but I just showed these compounds splitting into the ions. Now that I'm looking at this reaction with all the ions split up, I ask myself, what looks exactly the same on my reactant and product side? Okay, and I notice that bromine and calcium are both in their ion forms and in the aqueous state on reactant and product side. So that indicates to me that they are spectator ions, and so I'm not going to write them in my net ionic equation. Okay, and so when I write my net ionic equation, which is what is remaining, I'm going to have H plus hydroxide goes to water. Okay, and it's technically a 2 to 2 to 2 ratio, and so then you can just simplify it to 1 to 1 to 1. Okay, but what happens if we have a weak species? Okay, and so here we're going to react a weak acid, hydrofluoric acid, with a strong base, calcium hydroxide, to form water and calcium fluoride, a salt. So again, we're going to write any strong acid or base as their ions, right? Because they completely dissociate, and the salt also completely dissociates. Okay, so I'm going to rewrite this equation as 2HF aqueous plus calcium plus hydroxide goes to water plus calcium aqueous plus fluorine aqueous. Okay, now you might notice that HF I wrote as HF. Okay, and the reason for this is a weak acid, meaning if we have 10 molecules of HF, some will dissociate into their ions, but not all of them, right? Some of them will remain as HF as a compound together. Okay, and so because we're going to see some molecules of HF still together at equilibrium, we cannot write it as two separate ions. Okay, once we have the equation written like this, we look for things that appear the same on both sides, which in this case is just calcium, right, which is a spectator ion. And so I'm going to rewrite this equation without my spectator ions, right? So I have 2HF plus hydroxide goes to water and F minus. And so my net ionic equation would be my weak acid, hydrofluoric acid plus water, plus hydroxide goes to water and my conjugate base. Yes, strong bases have hydroxide. That was to a question in the chat. Okay, and here's just my last couple, this is my last slide to kind of really hammer home this example. Okay, so let's look at two weak acids, HA and HB, and I made up KAs for them. Okay, so because they're both weak acids, they're both going to have a conjugate base. So the conjugate base for HA will be A minus, and the conjugate base for HB will be B minus. Okay, because of my relationship between Ka and Kb, right, they always equal Kw when we multiply them, I can find my Kb for A minus and B minus. Okay, and all I want to show by this is HA has a higher Ka than HB, meaning HA is our stronger acid. Okay, but when we look at our conjugate bases and their KBs, right, the KB of B minus is higher than the KB of A minus, meaning B minus is a stronger base than A minus. Okay, even though HA is a stronger acid and B minus is a stronger base, right? Realize that both acids here are weak acids and both bases are weak bases. Okay, so B minus here is just a stronger weak base. Okay, the fact that it's stronger doesn't make it a strong base, it's just a stronger weak base. Hammering home, just another bullet point on spectator ions, right? So we'll see spectator ions whenever we have a strong acid, right? The anion portion or the conjugate base portion of a strong acid will be a spectator ion. And the cation portion paired with a strong base, right? So paired with hydroxide, that portion will be a spectator ion, right? So like sodium and sodium hydroxide, or in the previous example, calcium from calcium hydroxide was a spectator ion. Okay, and then lastly, remember that strong acids and bases dissociate completely. Therefore, on your product side, you should never form a strong acid or a strong base, right? Meaning your conjugate will never be a strong acid or a strong base because they dissociate completely, meaning it's kind of irreversible. You will definitely be using strong bases in this course, so I'm not quite sure what my wording was. Okay, but strong bases will have hydroxide as a part of it. Okay, here's a little table from a lecture that just shows different ways to describe strong and weak acids. Because I believe Dr. S went over this in lecture. Really, this is just be familiar with all this jargon, right? If they were to describe an acid in any of the ways listed, you should be able to use that fact to know whether it's a strong acid or a weak acid. So so strong bases don't form weak acids. Okay. Really, they just kind of dissociate into hydroxide. Yeah, kind of leave it there because it's tough. Because a lot of time, strong base like hydroxide will form water, and it's kind of hard to label that as a weak acid because water can be an acid or a base. So whenever I'm a little bit ambiguous, I don't mean to be. Again, acid-base chemistry is very, very complicated, and what we go over in this course is just a very skim overview of it. Okay, this slide is just to go over the acid-base properties of salts. Okay, and so what I'd say is that this bottom portion is the more important portion, right? If we ever see an anion, so it has a negative charge, right? Negatively, sorry, I've been talking chemistry so much and now my head's starting to get confused, so I apologize. So whenever we have a strong acid, the anion portion of the acid, which would be considered kind of the conjugate base, that will always be a spectator, right? So an example is Cl minus. Okay, if you ever see a compound with a positive charge, it is likely to be a weak acid. Okay, so if you ever see a compound with a positive charge, it's probably an acid, right? The best example of this is ammonium, NH4+, right? That is a weak acid. Now, bases, on the other hand, we associate weak bases with a negative charge. Okay, and so they're anions. And so a good example of a weak base is acetate, right? CH3COO minus. Acetate is a weak base. Now in this case, what I wrote here was potassium acetate, which is the salt form of acetate. Okay, so again, if you see a positively charged portion, it's often a weak acid. Negatively charged portions are often weak bases. Okay, but be careful. Negatively charged portions that are the conjugate of a strong acid is a spectator ion, right? Cl minus isn't really a weak base. It's kind of more of a spectator in this course, okay? While for bases, right, the cation or positively charged portion of a strong base will be a spectator, okay? And then lastly, some compounds can be either an acid or a base. And here are some of the examples listed. Okay, and so just some final notes. So percent ionization is it really, it tells you how much of the acid dissociates. So if I say an acid has 50% ionization, that means 50% of my weak acid dissociated into their respective ions. Okay, and so my general equation for this is percent ionization equals my concentration of H plus at equilibrium divided by my initial amount of weak acid times 100, right? The 100 just converts it into a percentage. And Ariana a while ago asked, how would you use percent ionization to determine the strength of the acid? Well, the higher the percent ionization, the stronger the acid, okay? And if you wanted to solve for a Ka theoretically, right, you could make up an initial amount of weak acid and use your percent ionization to find your equilibrium amount of H plus, and then use that value to find your Ka, which would also allow you to compare strengths of acids. Is H plus the strong base? No, so H plus is from the dissociation of an acid, right? So it's a product. It's the product H plus divided by my initial amount of weak acid. Okay, be familiar with amphoteric. That just means that the substance can be acid or base, right? So water, for example, is amphoteric. And then at the end of chapter 14, Dr. Katie introduced the common ion effect, right? And this is just a circumstance in which we have an ion that is added from two different sources. So often in this course, what we'll see is that the ion will be added in the form of a weak acid, as well as in the form of a salt. Okay, and so maybe in a certain situation, we add sodium fluoride to water. We also add HF to water. Okay, so in this case, we have a common ion of fluorine minus, right? That ion comes from two different sources, our weak acid along with our salt. And really, the important aspect of the common ion effect is that, or the important portion to keep in mind, is that we'll have an initial concentration of multiple compounds, right? Our HF and F minus in this case. Okay, and I'll talk about this more when I actually go through the challenge problems tonight. Okay, the last slide to go over, Lewis acid and base. So this is just a different definition of acids and bases. So a Lewis acid, by definition, is the acceptor of an electron pair. Okay, and so Lewis acids often have a positive charge. Lewis bases donate an electron pair. Okay, and so this definition, the Lewis acid base definition, doesn't involve the movement of protons, but rather involves the movement of electrons. Okay, and so the definition we typically use, where we look at the movement of protons, is the Bronsted-Lowry acid-base definition. Okay, and then my last bullet point is, don't forget that just because I went over these topics, there are other topics in both chapters 13 and 14. I did not go over absolutely everything that may appear on your exam. And so, for example, I guess I kind of went over writing net ionic equations tonight, but, you know, understanding that more in depth. There's a portion in lecture that they go over types of acids, understanding that. etc. There are other topics. So somebody asked, is the common ion effects an example of when you can use the Henderson-Hasselbalch equation? Could you use the Henderson-Hasselbalch equation? Probably. I think it just depends on the problem. So again, I'm going to have an example. In the challenge problems that I posted last night, there's a common ion effect problem. I think it's number 11. And so I'll talk about that more. I know I personally do not use the Henderson-Hasselbalch equation to solve that problem. However, yeah, it might be possible. I'd have to, sorry, my brain's starting to go. I've just been talking so much, so I apologize. Ozzy asked, will buffers be on the exam? So from my understanding, buffers are chapter 15, so they should not be. Somebody asked, can conjugate acids and bases be reactants? So I would never think about it in that way, right? I think of there is an acid and a base on our reactant side, thus our conjugate acid and conjugate base are on our product side. Really, the conjugate aspect is just saying that it's kind of the product, it's after it gained or lost a proton. Okay, so yeah, I would say that personally, I just always think of the conjugate acid and base as the product side. So Alyssa asked, is the Lewis acid or base the same thing that we've been doing? No, not necessarily. There are Lewis acids that are not Brownstein-Lowry acids, right? They're two different definitions of what an acid are. Okay, there are a lot of acids that apply to both definitions. However, there are, it's like a Venn diagram. They overlap, but they're not the same thing. In our course, when we do ice tables, we're using the other definition of acid and bases. However, they bring it up in lecture, so I wanted to bring it up. Hasib asks, are neutral solutions amphoteric? No, I wouldn't say so. So amphoteric is an adjective for a compound. Okay, so a compound is amphoteric, not really a solution. Okay, so water is amphoteric because it could act as an acid or a base, right? Bicarbonate, HCO3 minus, can lose a proton, so it can be an acid, but it can also gain another proton to become carbonic acid. So something like bicarbonate or hydrogen carbonate, same thing, that is amphoteric. Okay, it just means can it act as both an acid or a base in its natural state or in that current state. Victoria asked me to go back a couple slides, so yes. Oh, I'm sorry, I hit something. So for the question sent into the chat, I mean, so it's 40 degrees Celsius. So 40 degrees Celsius, it's not your normal conditions. So there are slight differences. And so there you would use your POH to solve for your hydroxide concentration, and then use your relationship between hydroxide and hydronium to solve for the concentration of hydronium. Right, so looking at it, I would say the answer is probably D, because it's a basic. It could be B if you do the calculation, but yeah. So in that circumstance, right, they're telling you the pH and POH aren't 7. Okay, so then you use the POH to solve for the other variables. I'm sorry, Alyssa, can you explain? understand what it was B. Yeah, you have to calculate it. I was just doing it based on looking at it, right? It's basic, so yeah, B would make sense. Okay, so a lot of people are, I'll let you guys debate that question back and forth all day. Yeah, I mean, people are saying it's D, which based on the calculations, that makes sense, right? POH is 6.8. So use the relationship between POH and hydroxide to solve for your hydroxide concentration. Hydroxide and hydronium always equals 1 times 10 to the negative 14. So then you can use that, and yeah, I think D would make sense calculation-wise. Two-step equilibrium to get practice. I went over polyprotic acids on March 5th would have been the session. That's the first time I brought it up. Okay, without further ado, I'm going to end the recording so that people that are watching this late don't have to hear the misery of my voice continuing to talk. But I am happy to stay and answer any questions if others persist. As soon as I finish this recording, I will begin uploading it and we'll finish writing out the solutions to the challenge problems. As quickly as I finish writing out the solutions, I will take pictures, get them up in the slides, and then record me talking through them. But it might take me a little bit to get that done. I'm going to do it as physically quickly as I can. But if you couldn't tell, my brain functioning from when I began this session till now seems to be a very heavy decline. Okay, so I'll probably drink some water and try to get back. But again, I'm going to end the recording. I will get both of the recordings up as quickly as I physically can. They'll be posted on the SI information tab in SI videos folder. Okay, best of luck studying, everyone. Best of luck on the exam tomorrow. Again, my email's different. So my email's ryan.p.2.kelly@uconn.edu. I know these sessions are kind of last minute, or a little bit later than normal. So if you do have questions, I will try to be really good about responding the next couple days over email. Okay, again, best of luck.